How's it going, guys? So here we are, chapter 1.2, and we are going to cover a catalog of essential functions. So remember, a mathematical model is a mathematical description, often by means of a function or an equation of a real-world phenomenon, such as the size of a population, the demand for a product, the speed of a falling object, the concentration of a product in a chemical reaction, the life expectancy of a person at birth, or the cost of emission reductions. The purpose of the model is to understand the phenomenon and perhaps to make predictions about the future. Figure 1 illustrates the process of mathematical modeling. So we're always, every time we're dealing with modeling or mathematical modeling, we have a real world problem. We then take it and we create a formula to help put that in terms of mathematics, right? Then we solve it. We have our mathematical conclusion, and then we reinterpret that conclusion, and what we get is, a prediction for the real world. And then this cycle just continues to go over and over again as we continue to use math in this modeling process to come up with predictions and conclusions. Now remember, there's always error involved in mathematical modeling. There's always error involved in a situation in which we are estimating. So a good model simplifies reality enough to permit mathematical calculations, but is accurate enough to provide viable or valuable conclusions. It's important to realize that the limitations of a model, in the end, Mother Nature has the final say. So, we're taking, more often than not, we're taking scenarios or situations. We're creating a mathematical model out of that particular scenario or situation that could be related to other situations. And then we're trying to use that information that we gathered to inform future decisions. But like they mentioned, there's always the possibility for mathematical error. Linear models do this for us tremendously. And a linear function helps us to do that. So we have y equals mx plus b, or f of x being your value of y, where b represents your y-intercept and m represents your slope, your rise over the run, your change in y over the change in x. And we see, a simple linear equation graphed, and then we see the table. Notice that whenever x increases by 1, the value of f of x also increases, right? So 0.1 to 0.3. But that essentially is where our slope comes from, okay? We have a couple examples here. As dry air moves up, it expands and cools, right? If the ground temperature is 20 degrees Celsius, then the temperature at a height of 1 kilometer is 10 degrees Celsius. Express the temperature as a function of the height. They want us to draw the graph, and they want us to know what the temperature is at the height of 2.5. So if we're assuming that t is a linear function, then we can create a linear function where you have t and h. H represents the height, and t represents your, let's go back here, t represents the temperature, obviously. So based off of the height, we're going to get a different temperature. And so we can plug in, we can solve this linear function, we can create a function where we're going to figure out what the temperature is with respect to the height. We can also graph that function, and we can see along this line what those different points are and how the height affects the temperature. At a height of h equals 2.5 kilometers, we can say that the temperature is negative 5 degrees Celsius. If you plug negative or 2.5 in here, you're obviously going to get that answer for the temperature. If there is no physical law or principle to help us formulate a model, we can construct an empirical model which is based entirely on collected data. We seek a curve that fits the data in the sense that it captures the basic trend of the data points. Now, a polynomial function plays into a lot of what we're talking about, especially when it relates to sketching, creating different functions that behave in different ways. So A function p is called a polynomial if it has many terms. So poly meaning many, so we have many terms here. Okay, n is a non-negative integer. A sub 0, a sub 1, a sub 2, a sub n are the constants, or essentially the values that fall in front of the variables. All right. The domain of a polynomial is always all real numbers, right? So we're going from negative infinity to positive infinity. This cool little r we typically write to denote real numbers. Okay. And then the coefficient a sub n does not equal 0, because if it does equal 0, then we're going to have nothing for that final term. Or 0 essentially would be it. So for example, here is our function. We can say based off of this function that this polynomial has a degree of 6. The reason we say the polynomial has a degree of 6 is because it's the highest degree term of all the terms in the polynomial. Degree, there's no degree here because there's no variable. Degree, third degree. Degree, fourth degree. Degree, sixth degree. So this is a sixth degree polynomial. A polynomial of degree 1 is of the form p of x equals mx plus b, and so it is a linear function. A polynomial of degree 2 is a parabolic function, or another word we use to refer to a parabola would be a quadratic function. It's a graph, so like I said, it creates a parabola, all right? And then we simply shift that parabola based off of the function. So notice this would be shifting the parabola up and to the left, okay? This would be flipping it and then shifting it up and to the right, okay? And notice this is the expanded form of that parabolic function. One thing that we may or may not do going forward is if we were to take this and complete the square of this function, then we would actually see the standard form of a parabolic function. I'm not going to get too much into that now unless we need to. I don't want to cloud us with those pieces. And then a polynomial of degree 3 can look something like this, right? And in all cases, notice these are functions, and they're functions because they cross the vertical line test. If I draw a line straight through any of these, in any place, it's only going to cross over one point on this particular function. And we can see the different values, the different equations for each of these functions and how they behave. For this particular class, and I got to be honest with you, I'm kind of surprised we didn't, but because the guy who taught the class before me did not require a graphing calculator, I have not, but I find a graphing calculator to come in handy tremendously, especially when we're talking about calculus here. And if you have one, I encourage you to plug these values in and see how they behave. Maybe even take your cursor and trace that cursor on the function to see how your values of x and y change based off of where the point lies. So this one, we have a quadratic model. A ball is dropped from an upper observation deck, 550 meters above ground. Its height h above the ground is recorded at 1 second time intervals in table 2. Find a model to fit the data. So basically what we have here is we have different points. And what we can do is we could find a model to fit this data. 0, 450, 1, 445, 2, 431, and so on. So if we were to go ahead and plot these points, we would notice that we have a scatter plot here, okay? And we can see that my graph is forming somewhat, of maybe a parabola, okay? Now, the only problem here is this, is that we know that we're not going to have negative time, so therefore we're not going to have this other side of it. The reason we're not going to have this other side of it is because obviously we don't have negative time. We're starting it at this point. We happen to be, 400 plus meters off the ground, and we're dropping it. And then time only goes up from that point. It doesn't go down. Okay. Now, what we can do is we can come up with a quadratic model. So using a graphing calculator, and this is something that I'm sure many of you have done before, but if you were to go ahead and plot all those points in a graph, what you could do is you could then take those points and arrange it using a quadratic model. One thing that we could do during our class on Thursday, if you have a question like this, I can walk you through how to calculate that on a graphing calculator. The one that I use is a TI Inspire, but just about any of the graphing calculators. I think when I was in high school, I had a TI 82 or something, TI 83 or something like that, and they work just as well. But when you do that, we can create a quadratic function. No, when h equals 0, that means that's where my graph is going to cross the x-axis, h being your value of y. All right, so what is my time t? How long is it going to take for that ball to hit the ground? Okay. The quadratic formula will also allow us to calculate this. So if we go back, if you remember the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. If you were to take that formula and you were to go ahead and plug it right into the quadratic that is on the previous slide right here, this being a, this being b, this being c, we could then figure out what our values of t are going to be. And when you plug that value of t in, yeah, you're going to get a negative and a positive number, but obviously only the positive value of t would be the one that we would use. Okay. Now we're just going to talk and review power functions. So a function of the form of f of x equals x to the a. Remember, a represents a constant, and it's called a power function, right? So that constant value, it could be, 1, 2, 3, 4, 5, whatever it is. All right, there are polynomials, with only one term here that behave in a certain way. This is our standard parabola. This is the line y equals x that cuts the first quadrant and the third quadrant diagonally in half, right? Slope of 1, exactly. But these are some power functions. And I would say that these functions are ones that you should have in memory and that you should just know how they behave, okay? We have y equals x to the fourth, y equals x squared, y equals x cubed. We use less y equals x to the fourth, but that's still 1. Y equals x to the fifth, and so on. And when you plug in those values, we can kind of see how our function, bends, changes, and behaves. The general shape of the graph f of x equals x to the n depends on whether n is even or n is odd. If n is even, then we have an even function as a graph is similar to a parabola, right? But if it's odd, the graph is similar to y equals x cubed. So you'll really see that there's those two functions. Y equals x squared, which is a parabolic function, and any even function will look similar to that, or even powered function, and every odd powered function will look similar to y equals x cubed. So if we go back real quickly here, basically we're focusing on this and this. And notice that the odd functions, powered functions look similar, and the even functions look similar. They behave similarly. Okay. And now you can see kind of how it adjusts based off of different values here. We can see how it changes slightly and bends, right? We can also see the square root function, which we learned the other day that if we had, the other half of the square root function or negative square root of x, it would provide the other side of what we would call a horizontal parabola. Okay, essentially it does end up being somewhat of the inverse function. And then we also have the cubed root function, which looks something like this. Okay, so we're starting to see a pattern here, which, when you have an even root, or let's start out with power, when you have an even power or you have an odd power, when you have an even root or you have an odd root, there are similarities in how these functions are graphed. And then we have the reciprocal function, which I like to refer to as our rational functions. When you have reciprocal functions or we have rational functions being those functions that can be written as a fraction, we get something that you would call an asymptote. More often than not, it's a vertical asymptote, but there are horizontal asymptotes that also present themselves. Okay? And, we're getting into rational functions here, p of x over q of x, and then we have our algebraic functions. Okay? Now, We're going to need to take, I would say, a little bit more time on the trigonometric functions, your sine functions, your cosine functions, how these different functions behave, but I'm going to strongly recommend that you review them. And then we also have our exponential and logarithmic functions, okay?